in some of the concepts we've been working through and so on in the last couple of sessions. I almost said weeks, but it's more like months. Okay, so it's a very simple model that we can show a couple of interesting contact effects on. So if I activate the different contact bodies, there are two contact bodies, and as you can see, there's a crack in the model. If I plot the outline, it's not connected there, so it'll open up a crack effectively at that location. The loads and boundary condition is very simple. It's constrained at the bottom, and I'm applying a boundary condition at the top. Just switch to that one, where I move this down a little bit and I move this in a little bit. So what we expect to see is that crack to open up and this load to be nicely transferred from the top to the bottom section. What is set up in the model currently is, let's go back to this view. You need to see the elements a bit later on. So what I've got is the materials are set up. I've got the load, the tables. If you look at the movement, I move it by 0.01 with the table, so that's all set up. What I need to define is the load case is defined. I've got the contact bodies, just the job that's still missing. The load case is very simple. I just selected the two boundary conditions. Effectively, I don't have a load, it's a movement boundary condition. I haven't tightened the tolerances. If you want, I can tighten and show what happens. Since this is a very simple model, it shouldn't make much of a difference. Okay, so let's start by not creating a contact table, and we see what happens if you use default contact settings. So I'll create a new structural. I select this one. We can ask for stress results so that we have that at least available. Then we run the analysis. Okay, so the model is pretty quick. It's set to run 10 steps. So if I change to contact status, so as you can see, the bottom part makes contact to the top. The top sits over there, which is why that node doesn't make contact. I haven't, it may actually make contact itself, to be honest. I haven't even checked or worried about that. But let's look at the deformation as I ramp this up. So you can see I've added significant deformation, moved it quite a bit, so it's about 10% of the size of the element. So there you can see that crack opening up nicely, but that is definite worry. So that it doesn't make sense. Same goes on this side, and it kind of fell off over there. But apart from that, it looks vaguely reasonable. So let's talk about why this happened. So firstly, this is node to segment. And since it's picked the bottom to the top, that node can catch nicely in that corner. So no surprise there. There's no node to touch on this face, and this one makes contact on that bottom face. So that's why the top part penetrates into this one, simply because we're taking contact from the bottom to the top. Even if it tries to do double-sided contact, it can't add this node from the top body into contact simply because that node and that node is effectively already in a different set of contact equations. So we'll form a circular dependency. So let's do something simple first. We go to contact and I add a new contact table. And just to show that we get the same response, I'll define a contact interaction, create a new setting, a touching contact, and I use exactly the default settings. Let's just call this touch, but it doesn't really matter. It's just easier to debug later on. Okay, so to include that, I need to, in the load case, specify that contact table. And the same in the job, specify that as the initial contact table. Okay, so I expect to see the same result, so let's just double check that it's at least the same before we start changing things. Okay, and we activate contact status again, and we go to the last step. Okay, so as expected, that penetrates. This one kind of moves in. Now, let's start thinking about ways to fix this. So the one would be to say, if I activate the option to extend the edges, this should work. So that node will then stay in contact with this because that last element will be extended a little bit. Let's see if that works. The defaults may just be not enough, but we can easily fix that. So contact table for this one, tangential extension. So the default is, I think 10%, and we're moving it by about 10%. So let's rather override this slightly. Just not certain whether this is a fraction or I think it's directly a unit. So this will be 0.015 should work. I've moved the top by about 0.1 to the left, so this should be more than enough. So let's see if this works. Well, that's just to try and fix this. It may do something on the left-hand side. Let's see. So we open the results and have a look at the results again. So initially that looks good. And at the end, no, that makes more sense. So this node has moved past, but it still makes contact with that face of the top part. In this case, it actually fixed this one nicely as well. So it doesn't always work this well, but in this case, it worked really well simply because that node can now make contact to that extended edge. Good. Now, let's say for whatever reason, this node was further along and I can't use that option. So let's look at different options to see what would work for node to segment. So I just edit this again. So we switch off that extension. What would happen if I swap the contact around? So let the top touch the bottom one. So let's see if that works. So again, in the contact table, I open this and I simply say I want the top to touch the bottom. So it's the second to the first. I change it over there. Okay, so there I'll see the bottom cannot touch the top, but the top can touch the bottom. That's why that part has disappeared. So I run the analysis again and let's see what happens. Just thinking what the easiest will be. Okay, instead of doing that, let me do something slightly different. So change that back to how it was just to make it easier. Let's copy this rather. Create a new contact table, and we'll copy that one as well. In case we need to edit it, for the moment, I don't think I'll need to do something. Let's call this touch 2. But I just add underscore at the beginning as a reference to myself that I'm not using it currently. In the contact table, I'll call this contact table 2. And this one I'd rather then specify second to first. So the first one stays the same. I can copy the load case. Call this load case 2. And I change to the second contact table. So the only reason I do this is it makes it easier then to swap between the different jobs and load cases without having to reset up anything. So I just copy this, and then I'll call this job 2, and I refer to the other contact table 2, for the initial contact. Okay, so I run it again. Bear in mind I don't have that extension on now. So put the model. And we look at the results. So contour bands. At first glance, this looks really good. So all of the nodes of that top section is making contact. But I go to the end, and that's really worrying. And that too, at least on this side, I don't have any issues. So what happened in this case? Why do we have this weird behavior of this penetration? The argument is this node is making contact to this face. It is not making contact to that top one. I can only make contact from one node to one face, so this doesn't work. At the top again, the node of the top part is making contact on that long face, but it's not making contact to the top as well. Well, if we make contact from the inside to that outside, that corner there is effectively the same for both of them. So that works better. But from outside to inside, I get really weird behavior at that side. So while I get better on this side, again, I can have a look and see if let's see if it works. If I extend the edges again, so I go to the contact table. In this case, let's use this one. I'll use that extension. Now I'm actually going to use it physically. So in my contact table, I refer to that one instead. So I want to sign existing. I pick the second one. So all I did was I used that extend edges, and let's see if it fixes anything in this model. Okay. So contact status, next step, go to the end, and it didn't fix anything. Kind of as expected, because that node at least cannot make contact in that phase. There's a small chance that something would have changed there, but it effectively in this model didn't actually fix anything. So swapping them around is definitely not a good solution. Now, if I go to the first one, I can actually make a difference and say, let's copy that same job. Let's call it job 1, and I'll refine in the name. I'll show you why I do that now. So now I can specify some kind of a measured activity. So the idea is, if I make contact from there to there, the issue was this node initially didn't make contact. So if I have more nodes there, it should look better. So let's try that then. So I go to measure activity. I specify local adaptivity. We'll see what it looks like in a moment. And I specify nodes in contact. So for that, I need to pick this bottom section. So identify, so there you can see the bottom. I'll select the bottom elements. And there I can say refine these. And I define the one with the nodes, not the one with the faces. So the green one's nodes will project against the blue one's faces as in the original model. And I specify arguments like a second level refinement. Okay, so we'll see what first and second level looks like. Don't ever make this much larger than 1 or 2. If you try and make it 10, you'll end up with one X element converts into a billion elements. So it refines it by 10 times in every direction then. So in this case, I'm refining it and then refining it again in 2 directions. Okay, I don't need to change anything. The measure activity simply limits that you set. And in the load case, there's no option for local refinement. So if you have a local refinement, it's always active. So run. It runs slightly slower, and normal model, it may actually take a bit longer. But look at the refinement. So as you can see, it refined that element by splitting it, and then the next row it refined again, and then afterwards it stays the same for all of those. So if I go to the end, again, this element penetrates slightly, but that one actually makes contact where it's expected. This looks good. And on this side, it does penetrate slightly, but just the last one. But since this element is so much finer where it makes contact, it's much smaller problem compared to initially. So if I plot the contact status, I see something similar to before. So again, that other option should work where I use the option to extend edges, then this node should be making contact there. But with this fine mesh, it's not a good idea. Other ways I can fix this would be to manually move that node so that it's not at the corner slightly above. And the reason it's slightly above is unless I have that extend edges on, it'll again slide off and fall off. So if I don't do this, if I move it just above that, even if it slides a bit, it should be okay, as long as it doesn't slide enough so that it falls off. Okay, so that's for node to segment. Now let's save a copy of this file. Save as, and I'll call this segment to segment. And the reason I want to do that is I want to remove that adaptive meshing. I don't want this job. And I don't care too much about first to second or second to first. So I'll delete all the stuff that's not needed. I don't need that second contact table and the touching. So effectively, I'm back to my initial model where everything made contact to everything else. Can double check there. This, I didn't have that on. So that's exactly as if I didn't have a contact table. Okay, so let's just clear this. Okay, so the only change I need to make on this one is changing from node to segment to segment to segment. So now it's faces making contact to faces instead of nodes to faces. So that's the advantage. It should work better in the corners. The downside is it's a stiffness-based method. So I expect to see a little bit of penetration. So let's see what happens. Submit analysis. Open the results. Contour bands. In this case, you see the contact on both meshes. So both the top and the bottom has the elements in contact. So just to show the two parts, if I plot the elements just as an outline. So there you'll see the split line, there's that crack. So nodes on both sides are making contact. And it gets it from the faces effectively that's in contact. Okay. And we look at the last step. And I didn't refine. But from here already, if I don't zoom further, it definitely looks a lot better than the initial model. So this is pretty much the initial one, only segment to segment instead of node to segment. So in most cases, this may be a good answer. If I zoom in here a second, there's still a little bit of penetration. That may be too much, or it may be fine. It depends on the kind of model you're interested in. So if you're worried about this, let's try and make it a bit finer. So by the way, I haven't rotated it, but it's a full 3D solid model. It's not just shell elements or planar elements. Okay, so let's try and reduce that penetration. So I'll just copy the job. And let's call it stiffer. And I change the settings to say, see, for the segment to segment contact, there's a scale factor for that penalty. The penalty is simply the stiffness or indirectly the stiffness. Let's try and make it 10 times. I'm not saying make it 10 times in a model. This is just a very small test model to see how it behaves. So run the model again. So same as before, initially at least, and at the end, if I zoom in, you can see it's not exactly on top of each other. That's why there's slightly two lines, but I have to go pretty close before I see penetration. So there you can see there's a little bit of penetration of the one mesh into the other one. If I plot it in wireframe, it may be a bit more visible, but probably not, to be honest. Let's see. There you can see there's a bit of penetration. Okay, so the advantage of the node to segment, as I've said, is it's perfectly stiff. Wherever a node is in contact, there's perfectly zero penetration. While in this method, I still have to tighten it up to get the penetration as low as I'm willing to go. But if you're not careful with the segment to segment method, due to the stiffness, you can actually underpredict the stiffness of the contact region. So that's the, let's say, the upside of the node to segment relative to segment to segment. The segment to segment on the other end, the contact conditions is much easier and much clearer to set up. So it's easier to get a segment to segment model in theory running. In practice, you may have issues with that penalty stiffness. It's not something that works really well in all models. If it works, you usually get a decent answer. You may just need to tighten up that stiffness effectively. So let's talk about when that stiffness is enough or not enough. So if I go back to my original model, and let's open rather the one with the results, then it's a bit easier to see. I open the results for this one. I go to that last step. You see there's not a massive, but possibly a significant deformation there. So I've moved this down by about 1/10 of this element size, and if I compare it to this, it's a lot less penetration there than I've got over there. If instead of enforced motion, if I applied a load there, whatever load I've applied there will be transferred to this. So the exact distribution may be slightly wrong if the stiffness is not enough, but it will be pretty good still. If I apply an enforced motion and the stiffness is not enough, so let's do a model of that. So let's call this underscore V2, and there's the reason I call this V2. I use the version 2 settings. So the version 2 settings for segment to segment is somewhat relaxed. It should be less stiff. Just want to double check that, yeah, this is not scaled up. Okay, so this should actually penetrate more. So it tends to run a bit easier, but depending on how important that stiffness is, you may actually get a worse answer. So let's start there. And even from this scale, you can see this is significantly more penetration. So this is a lot more than the previous model was. The problem there is you can see that gap is of the same order of magnitude as actually it opens up less than what that stiffness allows. Let's compare this to the other models. So close the results. Open the initial ones, which is stiffer than this, but not the stiffest that we ran. And again, I get to the last step, and now I can see that gap opening there, or that overlap is significantly less than this, but it's still, I'd guess, somewhere around 10%, maybe a bit less than 10% of this. If I open the stiffest model, see that is now a really small amount compared to this. Let's say closer to 1% instead of 10%. So let's look at the stress results at this location. And yes, I know it's a infinite stress, so I expect it to not be perfect. Let's look at the 1 meter stress, for example. So okay, so let's switch off averaging. That's, by the way, not a good mesh for looking at stresses for at a crack tip. So let's switch off averaging, at least you can see the differences. So the stiffest model in this case predicts 4.6 gigapascal. Okay, so yes, I know it's a lot, but the intent was to rather visually show instead of scaling up results, because it's really difficult to visualize scaled up results. So remember that number. We open the original model, go to the same step, and we activate the same result, 4.46. So it's similar, not the same, but it actually looks like it's in a different region. Let's rather do this. Open the stiffest one again, and we'll only plot the elements in that region. Okay, so just over 4 gigapascal in that region. So then go to the next model up, open that results. So this is the less stiff for the default one. So model plot. Okay, and we again picked elements just in this region. So that's 3.8. So that's it. Was about 5% difference, I'd say, compared to before. But if we open the last one, I expect to see a much more significant difference. You can already see there's something seriously wrong there compared to the stress there. Even the stress in the corner is now 2.7 gigapascal instead of over 4. If I again pick the elements in this region, so the maximum stress isn't even at that corner, or it may be possibly even one off, but the stress there is significantly less. So that's the complication with segment to segment. It's a really good method as long as your stiffness actually makes sense. So just getting back to my original model, if instead I applied a load instead of applied enforced motion, all that'll happen is this thing will move more and will penetrate more, but the same load should be applied to that tip, so you should get closer to the answer. But the moment you have enforced motion, your stiffness is critically important. So in that case, you have to use higher stiffness for that jointed connection. Okay, so let's just compare this as well to the original model. So if I look at the first one with the bad contact status, so that we had, just trying to remember, this is the one I think, let me just double check, I think we had of this one, this one had the extend edges on. So this is actually probably the closest in terms of accurate. If I look at the stresses, of again the elements in just this region. So that's very close to what we had with a segment to segment with a stiffer properties. The default settings was, I think, 3.8. So there's about 4.1. At least much better than any of the others. Okay, so the last one is if I open this, and this is now where I've refined the mesh using contact, and this is actually an unfair comparison because if I open that refined model, the mesh is finer in that region. But even so, let's have a look at what the elements there say. Okay, so the stress is now higher, kind of as expected, but it's not at the tip as expected. So again, we need to refine even a bit more. So even these will ideally have to refine. Just select slightly further. You know, the issue is the crack is there, so ideally I would want to refine these elements as well. Okay, so that's just going through a lot of the options that's available in contact. Talking about them in theory is, well, just theory, and it often goes over your head. But you first need to at least see what's available, and then if you look at the model, you look at a practical example, it makes a bit more sense when you try to work through this. Okay, so I hope this session actually was useful and made sense to you. If there's any questions or anything you'd like to still check, now's a good time to ask.